Hello, and welcome to this special PCEA series of lectures on PCB design. Our objective in this 12-part series is to cover the basic steps of designing a PCB from start to finish. In this lecture, we're going to be looking at what is a schematic sizes, schematic best practices, flat versus hierarchical schematics, and then schematic design process. We've already seen in the previous lectures the 4 stages of our PCB design, and we're now going to be looking at the second stage of schematic, but just a short review here. The first stage being the library, the second being the schematic, then printed circuit board, and then finally the output documents. So what is a schematic? It is a graphical representation of an electrical circuit. Now, these graphics that are used are called symbols, they are a part of the models that each component will have. We discussed these in the previous lecture on components and libraries. The symbol has 2 main purposes. Number 1, to assist with creating netlists or connections, and then secondly, assist humans reading the schematic. Now, these schematic symbols can be basic symbols such as discrete components, which are your capacitors or resistors or diodes or different things. These are often referred to as potato chip components, but they can also be very advanced components, even being thousands of pins. So although this is a graphical representation of an electrical circuit, it's important to understand that the components connected in a schematic diagram do not particularly correspond to the physical arrangement in the finished device. And this is a great example that we're showing here. Here we have a circuit diagram, and we have over here then what would be the PCB layout of this circuit. And there may not be a correlation between there. It may be that we have the connections that are between the schematic and the physical layout of the board. The schematic will not correspond to the physical arrangement in the finished product. So just kind of keep that in mind. Let's look at some international trade associations that dictate to the industry standards and guidelines that should be followed. The first one is the ANSI, or American National Standard Institute. Then the next is IPC, Institute for Printed Circuits. And then finally, IEEE, an Institute of Electrical and Electronic Engineering. 3 international trade associations have developed standards that the industry will follow. So let's look at schematic sizes. Schematics have been around for some time. As our industry has progressed, we have seen a major change in the development of schematic and the sizes of the schematic sheets themselves. For an example, schematic sheets can come in a variety of sizes, including and they're marked according to ANSI, which is your American National Standard Industry, which is A, B, C, and D. And they range from 8.5 by 11 to 22 by 34 inches. It used to be where you had to print out very large schematics. There was a lot of the tools were not keeping up, particularly with the ability to do hierarchical designs or different things like this. So what had to happen was the entire schematic would have to be put onto a single sheet. And a lot of times these were then done on printers that would print out these schematic sheets themselves. Well, we've actually now got this rather narrowed down to a couple options, and they are the most popular ones now, which is 8.5 by 11, which is the A size, and then 17 by 11 or 11 by 17 B size. These are now conventional sizes of paper that can be printed on a regular printer. So this is why we don't see too many of the other sizes anymore, is because they have kind of gone obsolete for our industry. So let's look at some requirements. Here we have an example of a schematic sheet. It's always important to kind of have a basic framework to work from on a schematic. I would put these as requirements that would be necessary on every schematic that you do. Number 1 is you need to have a confidential statement. The keep in mind that the schematic where you are developing will have intellectual properties that will be tied to your company. A lot of this will be things that you will not want to share with the industry. And this is, by the way, the schematic is one of those documents that is very highly protected because it does have basically your entire design in a sheet form. So definitely have this confidential statement on there. Next is a revision block. There will be revisions done on this design, on the schematic document itself. So it's important to document these changes. Now, these are often changes that will be done through what's called an ECO or an ECN. So that stands for an engineering change order or notification. And this is where that would be documented, so you can actually reference that ECO number back to that document, and then there will be more details then of what the changes happen, why did the change occur, and different things like that. The final item here is your title block. Now this holds some really vital information. This gives you your name of the document. It will give you your drawing number, your revision level that you're at, how many sheets are in this document and such. It also then will show who this was drawn by, checked by, and who the engineers might be. Now this title block, there's actually two types of title blocks that are used on a schematic. The first is ANSI, and this is actually a very, very good title block, and will actually hold a lot of information. The other option is called the standard title block. And this has a little bit less information, but it's perfectly okay, and it still works great. Now, a lot of times, companies will create their own title blocks. So it's perfectly okay for your company to create your own title block and to use that. So let's look at some schematic best practices now, because as we get into setting up our schematic and we then begin to look at laying down beginning to place our components and wire them up and different things like that and keep moving our project forward, we want to start this with some best practices, and it all begins in the schematic. And I want to really kind of bring this point out to you. It's about clarity. It's about having clarity in your schematic and having things clear. A couple things here. First off, know the function and flow of your circuit. Many times designers do not know the function of the circuit they are designing. So it's very important to understand that first off. If necessary, get into the data sheets, understand what the components that you're working with do and what that circuit is supposed to do. Secondly, understand the power and voltages. Now, as we're going to see here, they should be placed in a particular area, which will be on the top. Then your lower voltages, or grounds, or better known now as return paths, they should now be on the bottom. And also then understand there's a logical flow left to right on your circuit. Let me show you what I mean by this. Here we have a bad example of a circuit. This is a simple common emitter amplifier, but as you can see, it is very messy, as you can't understand where things are connected or how they're connected. This is very, very difficult to read this schematic, and that's a really kind of a term that's used as far as reading a schematic. So this is actually the same schematic if you look at it. But it's organized in a way where, first off, you have your power at the top and then your ground at the bottom. So there's a flow vertically between power and ground, and then there's a flow from the input to the output from left to right. Now, this is a rather simple circuit, but you could actually see the same thing here in this circuit, a rather more advanced circuit. Once again, you have your power at the top and ground or return paths at the bottom, and then the input should be in your left and then your outputs on your right. So there's a flow to the circuit. So understand that. Another point I would like to make regarding this point of clarity is the fact that you want to use consistent symbols for the same device. Don't Here's, for example, a resistor that is one type of graphic, and there's the other type. Use a single type of graphic when you're doing your schematic. This will definitely help in this question of clarity. So some other points: use unique designators for each component, orientate component text so it's easy to read, and place your decoupling caps by your part. So we'll discuss decoupling caps more at a later date. So there is two types of schematics. Number one, there's a flat schematic, which has each page standing by its own. Now in a hierarchical, you have then each of those pages represented by a schematic sheet on the front page. Now this is very convenient because you can develop your block diagram for your schematic, and also then you're able to create rather complex circuits because of this. By organizing your schematic hierarchically, you can then set up sections of your design and then place them together as a block diagram on the very top. So this allows you for multiple levels of hierarchy in development. So you can actually have you can even have, we'll say lots of pages available for you. So this is an example of a computer board that has a hierarchical design, but as you can see, it goes on. I think there's a total of 52 pages to the schematic. But by using the hierarchy, it allows you then to create very, very advanced schematics and keep them organized in a great way. How do we get from a blank screen or a blank page into a schematic? Well, let's go through the steps here very quickly. Number one is you have your project set up. This is where you will then bring in your template. You will then fill in your parameter information, what information will be on the schematic itself, the schematic name, the part number, revision, and such. The next stage then is your component placement. This is where you will then pull from your library components and then place them on your schematic sheet. Thirdly is your schematic connections. This is where you will now make the wiring connections from component to component and create the electrical diagram. Lastly, then, you wanted to have a schematic verification. This is done as a gatekeeping item, and I will be repeating this throughout other lectures that we are presenting in this series, is that the schematic verification is a gatekeeping item, which means that you will not want to proceed into the next step until you have a clean schematic to work with, that you have a verification that all the electrical rule checks have been done and you do not have any problems. The last step then is to push this into your PCB. In our next lecture, we're going to be looking at placing our components on our schematic and looking at the importance of our grid, the review of our schematics best practices, placing your first components, and then additional considerations.